Hello, I'm Barry Sullivan, Program Director for ECEDHA, and I'm pleased to be here to introduce this spotlight presentation on emerging undergraduate lab concepts, which will be presented by Leor Grebler, the Academic Solutions Advisor for Quanser.
Thank you. Good afternoon, everyone. My name is Leor Grebler. I'm with Quanser. I worked with my esteemed colleague, Dr. Tom Lee, our Chief Education Officer, to prepare this presentation for you today. And for those of you who know us, Quanser has been at the forefront of developing tools for teaching and researching controls. And for those of you who don't know us yet, over 2,500 universities worldwide are using some type of Quanser equipment or software for doing teaching and research in controls, haptics, robotics, unmanned vehicles, and even biomedical engineering tools. So over the next few minutes, I'm going to be talking to you about some of the new paths that Quanser has been taking and some of the trends that we've observed emerging among engineering programs. And we're actually in a very unique position to be exposed to so many different engineering programs, and we've been able to gain some insight on some of the challenges that are experienced by these programs and come up with some ideas on what we can do to help engineering departments teach the next generation of students. So this all goes back to the philosophy that's guided Quanser since its founding. This is the founder of Quanser, Dr. Jacob Abkarian. And he was a professor at the University of British Columbia when he first launched Quanser and developed some equipment for teaching controls. And his philosophy was always that experiments need to really bridge the gap between the theory and practice. So there's been a universal and common complaint among industry that engineering students are coming out of engineering programs without the tools to really do the real engineering work. And when Quanser was first founded, that problem was actually becoming very significant, that the engineering labs that were being used at the time weren't really reflective of the work that the students would need to do when they graduated. So whenever we looked at developing new tools, we always said that there needs to be a clear connection between the theory that's taught in class and application through the form of an experiment. And it's not enough for there just to be an experiment, but for this experiment to actually be effective, it needs to be modern and relevant. It needs to have, some application to what the student is going to be doing after they graduate. As well, it needs to be hands-on. And we've probably heard that term a million times already today, but it needs to be hands-on. And for it to be really effective, it also needs to be fun. So with this in mind, we developed this set of tools. And we started off with what we consider to be Tier 1 experiments, which are the very basic introductory controls experiments, things that teach a student, what's a controller, what's feedback, why is this important? And when students were able to master this concept, they moved on to the more challenging experiments, things like inverted pendulums and gyroscopes that we considered to be Tier 2 experiments. And finally, towards the end of their studies, or when they moved on to graduate studies or doing research level, we came up with platforms for doing research in robotics and haptics and controls, and those were considered to be Tier 3. So this closely matched the traditional structure of an engineering program, where you start off first by teaching theory, then you provide some application through the form of an experiment, and finally, towards the end of the program, you put it all together in some type of capstone project where students can demonstrate their knowledge. So what we're going to get into today is some of the trends that we've observed among engineering schools worldwide and some of the challenges that they're faced. And one of the biggest challenges that we're seeing is the desire to really recruit the best, the most motivated students into an engineering program, and to really keep them there once they graduate. Once they get into the program. So that usually involves making sure that there always is an application to what they're learning. The next big challenge that we're seeing is that schools are really striving for excellence in research and teaching. And how we define excellence in teaching means that students are going to be given the tools that they need to be effective engineers when they actually finish the program. So they're going to be able to leave the program and actually be able to contribute to society as engineers. And beyond that, when we look at excellence in research, we're talking about really being able to advance the body of knowledge of in any particular engineering discipline and pull industry forward with some type of innovation. So the last area that we're going to look at is for challenges is the desire to reach new groups and new markets. And I probably visited over 100 universities throughout the U.S. and Canada, and I've yet to sit down with the engineering department chair who tells me that they have, so much funding available for undergraduate teaching equipment that they don't know what to do with it. So I wish it was the case. And if anyone here today has that problem, please talk to me afterwards. I'd be happy to discuss it with them and help them out. But the reality that you here in the room know even better than me is that it's getting more and more difficult to find funding for undergraduate teaching equipment. And there's even programs like NSF2s that's out there that are becoming more competitive. And even if someone is able to actually get these funds, it's usually not enough to sustain a program. So one of the things that we've seen some engineering programs do is actually develop new programs and new courses to actually reach new markets and bring in new blood to their engineering department. And we'll be talking a little bit about that, but some of the ones that we've seen have been K-12 programs or even industry outreach programs. So looking at all these challenges, we decided to look at the 4-year plus traditional program and see what are the areas of focus along the traditional program. So when we look at the first year, even beforehand, the big challenge seems to be on recruitment, getting the best students, and I actually wouldn't even say the best students, but the most motivated students in the door so that they can learn more effectively. And then beyond that, it's keeping the students in place. And if you go to the back of any first-year engineering program, and especially engineering core course, especially if it's any time before noon, you'll typically see students that look like this in the back, and I hope that's no one here today right now. But this is kind of the process of becoming demotivated, and of course students are getting really creative. In fact, there even are resources out there to help students to learn how to sleep in class. But seriously, getting students motivated and is really half the battle to imparting material. And a motivated student is better equipped to actually deal with the rigors of an engineering program. So towards the intermediate years, the challenge that we see is on university engineering departments being able to revamp their teaching tools. So making sure that their teaching tools stay relevant to industry. And beyond that, it's making sure that researchers have the tools to do effective research, come up with publishable data. And then beyond that, what we talked about briefly is extending the reach of an engineering school beyond the campus limits. So it's with these K-12 and industry outreach programs. So looking at all these different areas, we said, we've come up with a bunch of experiments already. How can we put them together so that they can effectively relate to each of these areas of focus? So we started to develop these different lab concepts, which we're going to talk about now. And one of the first ones we're going to get into is one that we call the Inspiration Lab. And this is really a different approach to the traditional freshman year experience. Now, typically freshmen come in and are shocked by the amount of theory that they have to go through when they first get into a program, and they see that the engineering that they're learning is actually very different than what they've seen on TV about engineering, or watched on YouTube, or even read about engineering, and they can be very quickly demotivated by it. Which is unfortunate because students today are coming in with an unprecedented amount of knowledge in computer programming and also electronics. They're working with things like Lego Mindstorms, or they're programming Arduino boards, or they're even involved in DIY drones. And these things are really whetting their appetite for an engineering education. And when they walk in the door, they set foot on campus, they're really smacked in the face with this theory, and it kind of sets them off kilter. And they also see kind of these older labs, or maybe just labs that consist of banks of networked PCs, and they could be really demotivated by it. So we're working with some industry partners as well as academic partners to develop a really lasting freshman year experience. And the idea is to take equipment that's usually reserved for later on in the engineering program, to bring it down to the first year experience, and then to expose students to a wide variety of engineering disciplines, and really get them excited about the path that they've gone down. And the hope is also that through these labs, they can develop an engineering sixth sense that they can then apply to other courses that they're involved in. So we have a few experiments in mind for this lab, and one of the candidate experiments is around earthquake engineering. So in this lab, students come in and they need to design a structure that will withstand an earthquake, and the goal is to really design the sturdiest structure. And here they learn the difference between simulation and experiment, and they're in different groups, so there's a competitive aspect to it to get them really excited about it. Another experiment that we're looking at is around sustainable energy. And in this experiment, students need to design the shape of wind turbine blades. So they look at 3D modeling and then 3D printing, and the idea is to produce the most amount of power from a wind source to power a small city. And again, there's a competitive aspect to this, and also it's very relevant to today's industrial problems. And then the last one that we're looking at is around telemedicine and haptics. So students have to develop a needle insertion simulator to help surgeons train on how to insert a needle. Of course, we're not encouraging students to play with needles or anything like that in their first year. That's not the point of this. But they get to learn robotics, tissue modeling, even looking at some visualization. So my apologies to anyone here who might be a little bit squeamish, but this is what it would look like. So that's the idea of the Inspiration Lab, really to expose freshmen to a wide variety of different engineering topics, get them really excited about the career that they're going in, and to also stick with the program much longer. The other kind of side benefit of it is to use these labs as a showcase to incoming high school students, so they can see what they're going to be doing when they actually get into the program. So another lab that we'll be talking about is the driving simulation lab, and this is a take on that traditional controls course, but we've added a very visual element as well as a very direct connection to a modern problem. So we've been working with the University of Toronto to pilot this course, and we launched it just in the fall, and already it's getting some very good reviews. So in the course, students do basic DC motor control, where they have to do position control and speed control of a motor. So they're working with real hardware, except the motors are being used to actuate a steering wheel and drivetrain of a virtual car. So first, students learn how to actually get the car to move, and then they can drive it around this virtual track. And then beyond that, they have to build an autonomous driver to navigate around the track. And then they tune that driver so that it can actually perform better. And lastly, this is really neat. They're all in groups working on this. They come together at the end of the course, and their autonomous drivers actually have to compete against each other. So it really gets them very, very excited about this. So this is actually how it looks when it's running. So you can see the two motors working. One is for the steering wheel, one is for the drivetrain, and that's the virtual track that's running in the background. So another concept that we're working on is called the Cornerstone Lab. So you have the Capstone Lab or Capstone Project. This is a Cornerstone Lab to really set the foundations for the students. And this is a modern twist on that engineering core, multidisciplinary course that came out of the original drafting courses and later turned into the CAD courses. And we're very excited to be working with the University of New Mexico and National Instruments on developing this concept, and really feel it's going to be effective at imparting core engineering skills to students. So this is how the initial labs look. We start off first with a video game-like simulation, like you guys saw earlier. And then we move into simulation with some hardware. And then we only look at the hardware. Then we look at sensors, and then we put it all together and form a project. And the reasoning behind this is that, at the beginning of the course, we really want to captivate students with this exciting, video game-like simulation, and really draw them into the depth of the material. And I wouldn't use the word lure, but actually lure might be an appropriate word here, lure them into learning. So how this all fits together is that we're working with National Instruments to integrate our experiments more closely with their very extensive line of data acquisition cards. And one particular card that we're going to be working with is something called the MyDAC, which might have been presented earlier, but it's a small portable data acquisition card. And in the next few months, we're going to be releasing a product that we call the MyPlan that will connect into the MyDAC. And what the MyPlan is going to do is simulate the signals coming off of different hardware sensors. So this will plug into the MyDAC, and the MyDAC will think that it's connected to a piece of hardware. And we really feel that this is going to open up a wide possibility of off-campus experiences for students. And the way we see this working is that, day one, a student goes into a lab, looks at the physical hardware, takes measurements, looks at the, let's say, specs of the motor. Then later on that evening, the student goes to their dorm room or the library and models the experiment. And then they actually test out their model on a virtual version of the hardware. Then the next day, they go back into class and they can compare their model against the actual hardware and be able to validate their data. So this is how it looks when it's all put together. So you can see the MyPlant and the MyDAC working together, and the visualization in the background that looks very much like the actual hardware. So we really feel this is going to give a complete engineering experience where it's going to free the students from the constraints of that 3-hour lab time block that students have to get all their work done in. So it'll give them a chance to actually learn the material, focus on it, take their time, and better absorb it. So the last concept that I'm going to get into is a project that a capstone design project that we've been working with the New York Institute of Technology to develop. And of course, a capstone project is required in almost all engineering programs. But with NYIT, we worked with them to make their capstone project more scalable and repeatable, but at the same time preserve that very unique and creative solutions that the students are coming up with. So in this project, the students have to build this 2-degree of freedom ball balancer. So they have this camera overhead, and they have these 2 motors that it's going to balance a platform. And they have to model a small engineering firm. And we thought to ourselves, what's an engineering firm that they can actually we could actually use to model for them? And then we looked in the mirror and said, oh, we could pretend that they're working for Quanser and go through all the same steps that our engineers have to go to in order to make a new product. So they have to come up with conceptual designs. They have to do things like modeling and create controllers for it, and they have to do manufacturing and 3D printing. And in the end, they get a very good glimpse into life as an engineering student and what it takes to actually do real engineering work. So I guess the last question we need to ask ourselves from all of this is, where does this go? And we looked at all these different lab concepts, and one of the things I guess we can take away is that there's a great new opportunity now to re-engage engineering students, to get them very excited about the career that they're going after. And motivated student is more likely to do better in class, and better engineer at the end is able to contribute more to society and make the world a better place. So this is a very exciting time to be involved in engineering education, and we have a lot to look forward to. Thank you very much.